Hello, calculus students. Welcome to an online lesson. This is our first lesson and one of probably only two lessons dealing with two variable statistics. Historically, our calculus course has only covered one variable statistics, but starting this year with the change in the syllabus, we are now doing a little bit of what they call bivariable data, bi meaning two, so two variable statistics. Today we are going to talk specifically about this mouthful here, the Pearson's product moment correlation coefficient. They're usually just called the correlation coefficient for short. And we're going to find this value using technology. Our learning success criteria is that we'll be able to interpret this correlation coefficient, know what it means. So find it and know what it means. But to start with, we need to get a little background on two variable statistics. So to start with our terms of notation, again, feel free to pause the video here and add some of this to your notes. Two variable statistics. We now have an x and a y, and generally we say it's the independent variable, which is usually the thing that you can't control. That goes on the x-axis or your horizontal axis, and the dependent variable, which is often the thing affected by the independent, is on your y-axis. I'm sure your science teachers have done an even better job explaining that, but for our context, that's basically all we really need to know. So independent would be things like time, heights, things like that, things that are usually out of control. And then the y is the thing that may or may not be affected, like profits, weight, costs, things of that nature. Though sometimes it's a little bit unclear which one's independent and which one's dependent. Again, if they give you an x value, we'll refer to that as the independent variable. Correlation. Correlation is a way to describe the relationship between the x and the y. If you have a bunch of ordered pairs on like a scatter plot, and we see that that scatter plot is going upwards over time, meaning that the points are moving in a generally upward trend, we say it's a positive correlation. If they were going downward, we'd say it's a negative correlation. If they're just totally random all over the place on an x and y axis, we would say there's no correlation. And if there's any sort of relationship, we'll usually say the word causal. One causes a change in the other. And we have positive correlation when we're going up again, and negative correlation when we have something going down. So to start with here, I'm going to have 5 statements, all of which are describing correlation. For each one of these, we generally use 2 words. We have some sort of modifier, an adjective, and then positive, or I guess in this case it'd be an adverb and an adjective, but 2 words. One describing how strong it is. High meaning good, meaning very linear, and one meaning is it going in an upward or downward trend, positive or negative. Low would be an example of one that's bad. It's not very linear. The points are more scattered, but there's still a trend, and we can see that it's going in the positive direction. No correlation means the scattering is random and it doesn't seem that there's any relationship. And then we have low negative, meaning that, again, it's a not very good correlation, so low or weak or bad correlation. And then it's negative, going in the downward trend. And then, again, high negative follows the same suit. So using those pairs of words, we want to describe these 4 graphs here. So if we look at this first one here, it's not a great correlation. If I had to sort of sketch a best fit line, and we'll talk more about that next class, I could do that, and we can see a trend of the data, but it's not great, meaning most of the points are a good distance away from the line. But there's definitely a trend. It's definitely positive, and so we would say that this would be like a low positive correlation. Part B, again, if I were to draw a best fit line by eye, we can see that's much, much better. In fact, most of those points are very close to the line, and so we could say that this is a high correlation. But what kind of correlation? We can see the line is going down, so high negative correlation. For graph C, if you look at that, you've got points all over the place. A very strange data. I could follow some of these points and sort of make a best fit line going there, but I could just as easily follow these points here, that trend, and just think of those others as outliers. And if you can write more than one best fit line that seems equally reasonable and they go in totally different directions, that's clearly a case of no correlation whatsoever. So that would be no correlation. And then last but not least, we have this nice positive trend here. So it's positive and it looks quite high to me as well. So we'd say high positive correlation. So that's what we talk about when we talk about correlation. And again, two words to describe it. High and low are a little bit less common. Usually they'll say strong or weak, but really we're just talking about a good modifier and a bad modifier and then telling the direction of the trend. Okay, and that gets us to our learning intention, which was Pearson's product moment correlation coefficient. Now, a lot of times they'll drop the product moment part, or they'll even drop Pearson's name and just call it the correlation coefficient. It's referred to with the variable R, and this is the formula, one of many formulas, in fact, to find R. You can also find it using standard deviation of the x and the y and something called covariance. But that's beyond the scope of this course. So we could do this. We could make a big table, sort of like we did for standard deviation, but we're not going to. You do not need to do this by hand. If anyone is interested at some point, I'd be happy to sit down with you and show you how we could do one of these by hand. But as we read through here, it ranges from 0 to -1 for negative correlation, and then it goes from 0 to +1 for positive correlation. So I'm going to start with the positive correlation. What we're talking about here is that from 0 to 1, 0 meaning that there's no correlation at all. It's totally random data, just random scatter plot. And 1 meaning that it's perfectly linear, perfect correlation. For example, if I had a scatter plot and all the points would fit exactly on the best fit line, like those do right there, that would be a correlation coefficient of 1, perfect. And then again, 0, we looked at an example of that on the last slide where there's no correlation at all on the points. Anything in between there, the closer you are to 1, the better the correlation. The closer you are to 0, the worse the correlation. But you can also have negative values. I mean, if it's positive, we have positive correlation. Again, if you had a number close to 1, like 0.93, that would be strong or high because it's close to 1. But it's also positive, so it'd be high positive correlation or strong positive correlation. If I had something that was close to 0, like, let's say 0.13, I would say that is very weak positive correlation. But they can also be negative, which means that if I had those same values, like a negative 0.93, well, it's close to -1. So in that sense, it is strong, but it's negative, so it's strong negative correlation, which would mean you'd have a scatter plot that was going down. So again, we range from 0 to 1. The closer you are to 1, the better your correlation is, the stronger it is, and it can be negative. I usually don't even think about the negative when I'm thinking about how strong it is, and then if it's positive, we know it's positive correlation, and if it's negative correlation. I have this little table here. You don't have to memorize everything from it, but we should understand the basics of this. Obviously, 1's perfect, 0's terrible. That doesn't happen with real-life data very often. This is a big deal right here. 0.5. Anything below 0.5, you're talking about weak correlation. Anything above about 0.87, so your high 0.8s and all of your 0.9s, these are some sort of strong correlation. And you don't need to specify if it's very strong or strong. If they ask you to describe the correlation, again, 2 words get the job done. So strong, positive, or strong, negative. You'll notice I put absolute values around all these R's because this table works for positive or negative correlation. Ignore the negative when you're trying to decide if it's strong or weak. And then it's this big range right here for the moderate correlation, anywhere from the mid 0.8s down to 0.5 would be moderate. So what you need to know, 0.5 and below is weak. High 0.8s, 0.87, 0.8 and above are strong, and everything in between is moderate. Now, how can we find this value using technology? I've got a simple little bit of data here. I'm going to show you 2 things. First and foremost, something above and beyond what we need. I'm going to show you how to actually put this in the calculator. and not just put it in the calculator, but make a graph of this data. I'm going to show you how to make a scatter plot on the calculator, which is not the most useful thing, but it's a quick way to make a graph for us. So we've got a fertilizer company, which is to determine the extent of correlation between the quantity of compound X used and lawn growth per day. So they've got this chemical or compound that they're making, and they're adding various amounts of it, 1 gram, 2 gram, 3 gram, or 1, 2, 4, and 5 grams, and then they're measuring how much lawn growth they had based on that. So we wanted to find out what the correlation coefficient was, and then we want to describe that correlation using the correlation coefficient. So to start with, I am going to make I'm going to put the data in. Let's start there. So the same thing we did on one variable stats, we're going to go to stat, edit, clear out these lists. Oh, that was actually the data we had in there, but I'll do it again and we'll put it in together. So we've got for our X is our list 1, 1, 2, 4, and 5. And then for my list 2, I've got 3, 3, 6, and 8. So just like we did for two variable stats with a frequency, we're just putting our two lists in, L1 and L2. Now, I'm going to make a scatter plot, which is a graph. Normally when we graph things on a calculator, we go to y equals, but since we're doing statistics, we're going to press second and then y equals, which is stat plot. I'm going to go to my first stat plot, which is currently off, and I'm going to hit enter, and I'm going to turn it to on. You can now see the flashing cursor is on. It automatically defaults to a scatter plot, but you'll notice we can also make a connected scatter plot or bar graphs or box and whisker plots. All sorts of things can be made on these calculators, but we're going to use the first option, which is a scatter plot. It defaulted to L1 and L2 for my data. I'm going to use the default mark as well, which is a little box here. So that's good to go. Before I make my graph, I should mess with my window. And you can see here that I have that little scatter plot going here, but I don't want to see all those negative values. So I'm going to go to Window, and you'll notice for our X values, we don't have anything below 0. So I'm going to start with 0 as my minimum for my X. The highest value of an X is 5, so I'll go one past that to 6. Scale of 1 is fine. Y minimum, again, I'm going to get rid of all the negatives and start at 0. And it goes up to 8 on my data for lawn growth, so I'll leave it at 10. Scale of 1 is good. And I go to graph. So here's my scatter plot. So what can we see from this? So they tried putting on 1 gram of this compound, and we got 3 millimeters of lawn growth. So they tried increasing it, and up to 2 grams of compound, and they still had 3 millimeters of growth. So they said, well, let's try a whole bunch more. And suddenly, when they put a lot more on, the 4 grams, we got 6 millimeters of growth. And then when they went up to 8 grams, they got even more. So that's really a good thing for the company, because in order to get your lawn to grow, you have to buy more of their product. So our goal today was to come up with the correlation coefficient. So how do we do that? We don't actually have to see this graph, but I just wanted to start off with that. If I were to draw a best fit line, you'll notice that I can get a best fit line that's very close to most of these values. So we should have pretty strong correlation. We can also see that that best fit line has an upward trend. So it should be some sort of strong positive correlation. And so that should be confirmed now when we get Pearson's correlation coefficient. To do that, you can quit out of your graph if you made that with me. We need to turn something on in our calculator. We need to go to the catalog, which is second, and then 0. And then we're going to go down to the D section for diagnostics on. If you just press the matrix key, it'll take you down there because that's your D key. And then I'm going to scroll a little bit further down to diagnostics on. That's what we want. Diagnostics on. Again, I got there second, 0, scrolled down to diagnostics on. And now I press enter. Nothing happened. I press enter again. It says done. You need it to say done. Otherwise, it didn't do anything. And what that's going to do is allow our calculator to give us the correlation coefficient. If you don't turn that on, it won't give you R. You only have to do that once. The next time you power on your calculator, diagnostics will still be on. It's sort of like when you switch your calculator from radians to degrees. It stays where you left it. So we're fine unless we reset our calculator or borrow someone else's. We're going to go back to the stat menu. We've already edited in our data. We're going to go to calculate. We're not going to select two variable stats or one variable stats. We're actually going to go down to this thing that says linreg parentheses ax plus b, which stands for line of regression, and we'll talk about that next class. But I'm going to hit enter. It's two variable statistics, so it should default to list 1 and list 2, but I'm going to remind the calculator that I have data in list 1 and list 2. I'm going to press enter, and you'll see right here at the bottom is my R value. Again, if you didn't turn diagnostics on, it will not give you that R value. It'll just give you the A and the B up here, which we'll talk about next class. So we have an R value that is very close to 1. It's positive, and so we can say this is very strong positive correlation, or I would be totally fine with this strong positive correlation on a test. Again, two words, one describing the strength, and since it's close to 1, this is strong correlation, and one describing whether it's positive or negative, and again, this is clearly a positive value. So that's correlation coefficient. One last thing to say about coefficient. We know that word coefficient from other math classes. The coefficient is always the thing that's in front of the x. If you think about a literature class or an English class, and when we have words in front of other words, like for example, if I was going to tell you a story about a rich princess, rich is the adjective that describes the princess. I put it in front of it. Well, a coefficient is like an adjective for math class. The 3 here, the coefficient of x, describes the x numerically, saying that we have 3 times the value of x, or 3 of those x's. And so when we talk about a correlation coefficient, the coefficient, again, is a number, but it's a number that describes the correlation. So in case you're wondering why we call this a coefficient, it goes back to that idea that a coefficient is like the adjective of math class. It's a number that describes things. All right. For homework, we just have a handful of problems, 5 problems here on 549 and 543, all dealing with correlation and the correlation coefficient. Until next time.